So these illustrations show a model for what's happening in the nucleus when it undergoes fission. Now I should point out that because it's so small, nuclear reactions, like atomic reactions, are dominated by quantum mechanics. And any classical picture like I draw here is at best a limited analogy, but it can still help us understand to some extent what's going on. So a neutron comes in, and as it's attached to the nucleus, that binds it in there. There's a lower total energy because it's now bound, and that extra energy excites the nucleus, making it oscillate back and forth. Now, because the nucleus is positively charged, this part of the nucleus on this side has a net positive charge, this part has a net positive charge, and those two sides will repel each other, trying to push apart. Of course, the reason the nucleus stayed together in the first place is that the strong force pulls those two halves together. But the strong force has relatively short range. So if these get far enough apart, the repulsion from the electric force will dominate over the attraction from the strong force. Once they reach that critical distance, the electric force dominates, pushes the two parts apart to the point that they actually split into two separate nuclei. And then the strong force pulls those two nuclei around into being more spherical shaped. Once they've split like this, generally these first two daughter nuclei are extremely unstable and will decay essentially immediately by ejecting out some neutrons. Also, just keeping energy and momentum conservation both consistent is easier to do when you have more constituents. So they're going to tend to spit out some neutrons to conserve both energy and momentum. Now you may ask, why is it that some large nuclei will undergo fission like this and others will not? For example, uranium-235 does undergo a fission, uranium-238 does not. Bohr and Wheeler, who developed this model here, came up with an explanation for that as well. They said, let's plot the potential energy of the system from a very small distortion parameter. The distortion parameter is how far apart these two centers of the two globs are. From a distortion parameter of 0 out to essentially an infinite distortion parameter. Well, whatever the difference in energy is between that initial energy, when you have a perfectly spherical parent nucleus, and the final energy when they're totally separated, that's the energy released, Q. But somewhere in between, the potential energy is going to go up. If it didn't, they would just spontaneously fission all the time. So we've got some barrier height. And the two halves have to either tunnel through the barrier, or they have to be given enough energy to jump up over the barrier. They are fairly massive halves, so for most materials, they won't tunnel through. There are some where they do, but for most, they don't. So we need to drop in a neutron with at least close to as much energy as this barrier energy, so that we at least get it up to the very top and then it can tunnel through. Or if we drop in with more than the barrier energy, we can get the total energy up and over the hill, and then it falls down, releasing the initial energy Q, or the reaction energy Q. We have here the values tabulated for a number of different elements, or isotopes. So here you see uranium-235, which becomes a 236, which fissions. The neutron, when it falls in, adds energy to the nucleus of about 6.5 MeV. However, it has a barrier height of 5.2 MeV. As a result, that is enough to push the system up over the barrier and make it fission. For uranium-238, the released energy from the neutron joining is only 4.8 MeV, and the barrier is now a little higher, 5.7 MeV. That's not high enough. We're still 0.9 MeV below the top, and we don't fission. Plutonium, the neutron adds 6.4 MeV, and the barrier is only 4.8 MeV. That's plutonium-239. And for americium-243, the neutron adds 5.5 MeV, but we need 5.8 MeV. So we still don't undergo fission by thermal neutrons. It's not coincidence then that uranium-235 and plutonium-239 are the isotopes that are used both as nuclear fuels and in nuclear weapons. We can make uranium-238 and americium-243 fission, but we have to hit it not with just low-energy thermal neutrons. We have to hit them with high-energy neutrons. That can be done, but it's a little more complicated, and while you can get the fission to happen, the probability of the neutron being captured and joining with the nucleus in the first place tends to go down.